Let's look at a few more examples where we use the fundamental identities to simplify trigonometric expressions. Here, the expression we're working with is cosecant x times tangent x plus secant x. Well, as we discussed in the last video, it can often be helpful to rewrite each of our trig functions in terms of sines and cosines. We can use the reciprocal identity for cosecant and rewrite that as 1 over sine of x. We can use our quotient identity for tangent and rewrite tangent of x as sine of x divided by cosine of x. And we can also use a reciprocal identity for secant of x and rewrite that as 1 over cosine of x. I have 1 over sine x times sine x over cosine x plus 1 over cosine x. This helps me out because I can now cancel out these sine x's. I've got a sine x divided by sine x. Those will divide to 1. And I'm left now with 1 over cosine x plus 1 over cosine x. Well, I have two fractions connected by addition, and I can combine two fractions if they have a common denominator, which in this case they already do. Well, if they have a common denominator, all I have to do is add the numerators. This gives me 2 divided by the cosine of x. And finally, we can use our reciprocal identity for cosine to rewrite this, our final answer, as 2 secant x. Notice here, this would be the same thing as 2 times 1 over the cosine of x, giving us 2 times secant x with that reciprocal identity. Here's our next pro tip. Do not leave trig functions in the denominator of a fraction. Here we had cosine in the denominator of a fraction. Instead, bring them to the numerator using reciprocal identities. All right, so I can instead rewrite this as a secant, the reciprocal of cosine, in the numerator. 2 secant x is our final answer. Cosine x times tangent squared x plus cosine x. Now, this is a problem where we certainly could rewrite our trig functions in terms of all sines and cosines. That's not necessarily the wrong thing, but here's one other technique that we want to become familiar with. Notice that each of the terms in each one of these groupings has a cosine x. Cosine x is actually a common factor between each term, and we can factor out a cosine x, leaving us with cosine x times tangent squared x plus 1. Yes, these trig expressions are going to factor just like our normal algebraic expressions would. If we had a greatest common factor, yeah, we can factor that out from our terms. Now we have a cosine x times a tangent squared x minus 1. Sorry, tangent squared x plus 1. Well, tangent squared x plus 1. We have squared trig functions and a 1. We should think of our Pythagorean identities. I can replace tan squared x plus 1 with secant squared x. This is now cosine x times secant squared x. That was my Pythagorean identity. Secant squared x, I can now rewrite using a reciprocal identity. Secant squared is going to be the same thing as 1 over cosine squared. I now have cosine x times 1 divided by cosine squared x. And one of the cosines in the numerator will cancel with one of the cosines in the denominator, leaving me with 1 over the cosine of x, which I can then use a reciprocal identity to rewrite as secant x for my final answer. The next pro tip, look for opportunities to factor out greatest common factors, right? In this case, each term that in my expression had a cosine x associated with it, we can factor out greatest common factors. Cosine squared x minus 4 divided by cosine x minus 2. On the topic of factoring, our next pro tip is to look for opportunities to factor trig expressions written in the form of quadratics or polynomials, right? Let's look for trig expressions that are factorable. More specifically, let's take a look at our numerator in this case, cosine squared x minus 4. Now, the related algebraic expression that you might be more familiar with would be x squared minus 4. Notice the only difference between these two expressions is that the top one has a cosine of x, quantity squared, and this one has an x squared. Well, You guys should all be comfortable factoring x squared minus 4. This is the difference of squares, which factors into x plus 2 times x minus 2. Our trigonometric expressions are going to factor in a similar manner, except instead of x's, we are going to end up with cosine x's. This gives me cosine x plus 2 times cosine x minus 2 when it is written in factored form. So what we have here is cosine x plus 2 times cosine x minus 2, all divided by cosine x minus 2. And the cosine x minus 2's divide out, and we are left with cosine x plus 2 as our final answer. All right, look for opportunities to factor. Let's do another one here. Secant to the fourth x minus tangent to the fourth x. Here is another opportunity for us to factor. Secant to the fourth x minus tangent to the fourth x. Now this one's a little bit trickier because I've got two different trig functions, but I could create a similar algebraic expression with just two different variables. X to the fourth minus y to the fourth. Instead of a secant x, I just have an x. Instead of a tan x, I have a y. Well, this is actually in the form of the difference of squares. This would be x squared squared minus y squared squared. As we saw before in the previous problem, the difference of squares factors into x squared plus y squared times x squared minus y squared. There's our difference of squares. And therefore, our trig expression here is going to factor very, very similarly. This is going to give me secant squared x plus tangent squared x times secant squared x minus tangent squared x. So we've got secant squared x plus tan squared x times the quantity secant squared x minus tangent squared x. Well, we've got groupings of squared trig functions, and more specifically, let's look at this one here, secant squared x minus tangent squared x. We had the Pythagorean identity. 1 plus tangent squared u was equal to secant squared u. Well, we can manipulate this equation and subtract tangent squared u from both sides of the equation, giving us 1 is equal to secant squared u minus tangent squared u, meaning that this entire portion of the expression actually turns into 1. And 1 times secant squared x plus tangent squared x leaves me with secant squared x plus tangent squared x. Oh boy, more factoring here. Let's take a look at this one. Cosine to the fourth x minus 2 cosine squared x plus 1. This expression is in the form of a quadratic. Now, it's a quadratic it's a polynomial, a quartic polynomial that's in the form of a quadratic. Here we have x to the fourth minus 2x squared plus 1 would be the related polynomial expression. Notice that instead of x's, we end up with cosine x's, right? Instead of an x squared, I have a cosine squared x. All right, and so these will factor in the exact same manner. X to the fourth minus 2x squared plus 1. Well, that's going to factor into x squared minus 1 times x squared minus 1. That means my trig expression is going to factor into cosine squared x minus 1 times cosine squared x minus 1. Or, more simply put, cosine squared x minus 1 quantity squared. So we've got groupings of squared trig functions and ones. Let's think about our Pythagorean identities. Our first one, sine squared u plus cosine squared u is equal to 1. Well, if I subtract 1 from both sides and subtract sine squared u from both sides, I get cosine squared u minus 1 is equal to negative sine squared u. Therefore, I can replace this entire quantity, cosine squared x minus 1, with a negative sine squared x. And what happens when I square a negative? Well, it becomes positive, and when I raise exponents to exponents, we multiply them. This leaves me with sine to the fourth power x. Let's do some more factoring. secant cubed x minus secant squared x minus secant x plus 1. Well, we've got our related polynomial. Notice this is a cubic polynomial, and this polynomial can be factored by grouping. Again, note the relationship. In my trig expression, instead of x's, I just have secant x's. Otherwise, it's identical. Well, what does my polynomial factor into? We can start by grouping our first two terms and our last two terms, factoring out our greatest common factors. That's x squared times x minus 1 times x minus 1, which factors into x squared minus 1 times x minus 1. There is our factoring by grouping. This means that our trig expression is going to factor in the exact same manner. We can start by grouping our first two terms together and factoring out our greatest common factors. We've got secant squared x times secant x minus 1 times secant squared x minus 1, leaving us with secant squared x minus 1 times secant x minus 1. We just factored that cubic polynomial by grouping. Well, we've got some pairings of squared trig functions and ones. That should make us think about our Pythagorean identities. We had the Pythagorean identity. 1 plus tangent squared u, 1 plus tangent squared u is equal to secant squared u. Therefore, tangent squared u is equal to secant squared u minus 1. Here we have a secant squared x minus 1. I can replace that with tangent squared x to give me my final answer, tangent squared x times the quantity secant x minus 1. All right. Last examples here. So, use the fundamental identities to simplify the following expression. In some cases, all right, all we want to do is perform the given operation. Notice here they are telling us to subtract. If I want to subtract two quantities, I must get a common denominator. My denominator of this fraction is tangent x. In order to get a denominator of tangent x, I must multiply by tangent x over tangent x. And that gives me tangent squared x over tan x minus secant squared x over tan x. Now that I have a common denominator, I can combine these two fractions into a single fraction by combining the numerators, and my denominator stays the same. Tangent squared x minus secant squared x divided by the tangent of x. Well, we've got a pairing of a tangent squared and a secant squared. Think again of our Pythagorean identities. 1 plus tangent squared u is equal to secant squared u. Well, we want it to say tangent squared minus secant squared. That means I need to subtract secant squared from both sides and subtract 1 from both sides. Tangent squared u minus secant squared u is equal to negative 1. Again, we have rearranged our Pythagorean identity, meaning that the whole numerator can be replaced with negative 1 divided by the tangent of x, and anytime we have a trig function in a denominator of a fraction, we can bring it to the numerator as a reciprocal using the reciprocal identity. This gives me negative cotangent x as my final answer. All right, so our last pro tip here, perform the given operation. Here they're telling us to subtract. Let's subtract. One more example here. 1 divided by secant x plus 1 minus 1 divided by secant x minus 1. Again, let's perform the given operation. They are telling us to subtract here. Well, if we're going to subtract these two fractions, we have to get a common denominator. I'm going to multiply this first fraction by secant x minus 1 over secant x minus 1, and the second fraction by secant x plus 1 over secant x plus 1. Now we have our common denominator, and we can now combine our numerators via subtraction. Well, a secant x minus a secant x. Those actually subtract out, all right? And I've got a negative 1 minus another 1. Well, that's going to leave me with a negative 2 in the numerator. And also notice that if I were to multiply out our denominator here, we end up with secant squared x minus 1. So this gives us negative 2 over secant squared x minus 1. right? The secant squared x minus 1 comes from foiling our distributive property of multiplication. Secant x times secant x is secant squared x. Our outer and inner terms add to 0. Positive 1 times negative 1 gives me a negative 1. All right, and again, as we said, secant x minus secant x, negative 1 minus a 1 gives me a negative 2. This is negative 2 divided by secant squared x minus 1. We have groupings of squared trig functions and ones. Let's think of our Pythagorean identities. Again, same one in this case. 1 plus the tangent squared u is equal to secant squared u. This means tangent squared u is equal to secant squared u minus 1. I can replace my denominator with tangent squared x. And for my final answer, I can bring this tangent squared x up into the numerator using our reciprocal identities, giving me negative 2 cotangent squared x. All right, that's all for chapter 5.1. A little bit of problem solving, solving puzzles. That's all, using those fundamental identities to simplify trigonometric expressions.